Good day. Let me introduce myself to you at the beginning. My name is Miriama, and I work at the Technical University in Kosice. Today I will present the results of our research titled Using Quality Management Tools to Analyze the Error Rate in the Production Process. The quality of production is currently a decisive factor in business. It is the basis of success in the market, and it is also crucial to the overall prosperity of the producing organization. This article examines the detection of the most common errors and their causes in the production process of printed circuit boards. Basic quality management tools were used for analysis and evaluation, namely FMEA, Pareto chart, and Ishikawa diagram. Through them, we identified not only problem points in the production process, but also measures that the organization subsequently introduced into the production process. The company in which error analysis was carried out in the production process using quality management tools is a manufacturer of industrial electronics. It has been operating in Slovakia since 2000. The organization has an integrated management system and holds certificates that demonstrate compliance with the requirements of the ISO 9001:2015 standards. The basis of production is 6 assembly lines, where the production of printed circuit boards takes place from their installation, testing, and final assembly to the delivery of the finished product to the customer. One of the production lines of this company analyzed in this paper is semi-automatic with manual production predominating. This is the finalization line on which PCB production is completed. There are 11 operators working on the production line. See Figure 1. They have workflows that describe individual work operations with the names and component labels for specific PCB models. Depending on the model currently being produced, operators choose a workflow and check the individual components. 3 selected quality management tools are used to analyze the error rate of a particular production process: FMEA, Pareto chart, and Ishikawa diagram. At first, failure mode and effects analysis is one of the basic tools applied within ISO 9000 standards. The aim of FMEA is to analyze potential errors in a particular system over a selected period of the service life of the system, so that corrective measures can be taken to reduce the risk that the emergence of errors entails. According to Stamatis, an FMEA system can be achieved using a series of steps that include conceptual design, detailed design, and development, test, and evaluation. Secondly, Pareto analysis is one of the most effective quality management tools, which makes it possible to separate the root causes of a particular problem from the minor ones, thus showing the direction in which efforts to ensure quality assurance in the process need to be focused in order to remedy its shortcomings. The Pareto chart was first used in quality management by Joseph Moses Uron. According to Douglas Montgomery, the Pareto chart does not automatically identify the most important defects, but only the most frequent. Thirdly, Kaoru Ishikawa developed a simple tool to identify possible causes of a problem, known as a cause and effect diagram, or a fishbone diagram. Very often a version of the diagram with the main categories of causes is used: people, material, machines, methods, and environment. The analysis and evaluation of the quality of the production process is divided into 4 parts. Analyzing the production process using the FMEA method. Evaluating the occurrence of errors using Pareto analysis and Pareto chart. Finding the main causes of the most common errors using the Ishikawa diagram. Proposing measures to eliminate the most significant errors. FMEA results. The aim of the analysis was to analyze the production process and to determine the occurrence of errors at the different stages of production. The main tool in the development of FMEA was brainstorming. The result was the determination of a risk priority number, which is expressed as the product of 3 indices: severity, frequency, detection, where each index can receive a score in a certain interval. In our case, the score is on a scale of 1 to 5, see Table 1. The resulting risk priority number value is between 1 to 25 points. FMEA pointed to some critical points in the production process. Based on the risk priority number index, a risk level was established. The mean level of risk has been identified at production stages such as material preparation, glue application, capacitor, filter, connector mounting. For risks exceeding a specified value of 15 points, include 4 functions of the process, see Table 2. For example, the installation of the fuse reached a risk level of 20 points. Cause of the failure: unwetted area when installed, resulting in malfunctioning PCBs. By supplementing pin tester, we will reduce the risk level to 10 points. FMEA pointed to some critical points in the production process. Measures to eliminate deficiencies were recommended for these production areas. The implementation of the measures has resulted in a significant reduction in the values of the risk priority number. Results of Pareto analysis. Data analysis was divided into 2 periods. In the 2019 year, in months, September and October, and in 2020, February and March. The errors observed, together with the degree of severity of the errors, are in Table 3. Error analysis focused on the production line system for hand-installed components on the printed circuit board, the final step of production. The degree of severity is expressed using a natural number between 1 and 10, with 10 being the most serious error. Figure 2 is a graph showing the occurrence of errors in the manual installation of components during the reference periods. A total of 1978 deficiencies were identified in the 2 reporting months of 2019. The most significant number is in the case of error 1, missing part, which accounted for almost 35% of the total number of noted errors. In the 2020 year, 1447 component planting defects were identified, representing a reduction of almost 27%. Again, the most significant number was error 1, missing part, which accounted for approximately 32% of the total number of noted errors in a given period. For evaluation using Pareto analysis, we chose the 75/25 criterion, under which it is recommended to monitor in more detail errors for which the cumulative relative number reaches a value equal to 75%. The results obtained show that the situation in terms of product quality has improved over a number of months. Absolute error rates, except for error 2, decreased significantly. In the case of error 3, the decrease is by up to 68%. An analysis of the production process showed that error 3 were mainly due to the cooler component, which has multiple connectors, is harder to install, and can get raised in the oven. For this reason, it was proposed to adjust the setting of the oven by changing the shape of the weights used to load the cooler before it enters the oven. The situation also improved with error 1, a decrease of almost 9%. In the case of error 2, the absolute number increased by almost 8% compared to the previous period. Therefore, for error 2, it was been proposed to add an in-circuit board tester control pin to check the length of the connectors. Adding this will extend the testing time, but will improve the quality of the supplied board. The Pareto chart shows that during the 2 months in 2019, 3 defects formed a vital group of causes of poor quality products: missing part, missing pin, and raised part. In total, these 3 errors accounted for up to 76% of all detected errors, see Figure 3. In 2020, the order of errors changed slightly. The vital group of causes consists of only 2 errors, missing pin and missing part, which represent up to 75% of all errors in the production process during the given period, see Figure 4. Results of Ishikawa diagram. The Ishikawa diagram, or fishbone diagram, is an appropriate tool for solving problems arising from the results of Pareto analysis. Under the chosen criterion, 75/25, it is recommended to address a vital group of causes of poor quality products in the next step of the evaluation of the quality of the production process. In the case of the monitored production process, these are errors, missing pin, and missing part. The basic subproducts for which measures have been proposed to eliminate error 1 or 2 error numbers are indicated in red. The cause most involved in the number of error 1 is the people category, where compliance with working procedures, necessary concentration, and length of training is crucial. See picture 5. The methods and machines category appear to be another problem. The basic subproducts for which measures have been proposed to eliminate error 2 are indicated in red. The frequency of error 2 was mainly affected by the method of packaging and handling during unpacking and transport. In the case of the machines category, the setting and maintenance of the tester, and also wear and tear of the control pin and the interval of its replacement and failure are significant causes. The category people mainly works experience, working discipline, focus on the work performed and adherence to the prescribed workflow. The proposed measures for the 3 most important main categories, people, machines, and methods, are summarized in Table 4. In the people category, we proposed these measures. Firstly, rewrite workflows into a more comprehensible and clearer form. Retrain operators and educate them about the internal rules of the organization. The second measure, inform operators about the number of errors caused by them and motivate them to work better. Thirdly, set up training rooms for newly recruited operators, where they will undergo 2 weeks of skills training before starting work. The individual procedures for analyzing a given production process identified errors for which it was necessary to design and take measures to reduce or eliminate them entirely. Using the Risk Priority Index, FMEA has clearly highlighted the critical points in the production process for which the necessary measures have been proposed to prevent these errors. The Pareto analysis identified the causes of key errors in the working environment, the error 1 and 2. For better diagnosis of the problem, for each major category of causes, subcategories were determined, supplemented by other minor causes with their share of the observed error. In both cases, it was confirmed to us that the human factor had a significant influence on the number of these errors. Therefore, human resources need to be given at least as much attention as technical equipment, finance, and other production capacities. Currently, a lot of attention is paid to the quality of any product. In addition to increasing requirements for increased and accelerated production, this is due to the growth of customer requirements for the quality of the final products. Deficiencies and defects will always appear in the production process. Defining significant errors and their causes enables your organization to focus on reducing or eliminating them. Quality management methods play an important role in the analysis and evaluation of errors. Thank you very much for your attention.